It gives me a great pleasure in welcoming all of you for the first program of the PALS 24-25 edition. So this is the first program for the year, and we are starting this program with this year with a power-packed session from an esteemed institution from IIT Bhubaneswar. So today's session is on digital design using Verilog, and that is by Professor Srinivas Boppu. Thank you for supporting PALS, sir, and thank you for coming for this program. So it gives a great pleasure in welcoming you. I also welcome the faculty and students from PALS partner institutions. A few of you, I assume, that are attending the PALS program for the very first time. And I hope, we hope that, you can hugely benefit from this collaboration. So it gives me a great pleasure in welcoming all of you also. PALS champions, if I know that Anu is there. So welcome to Anu. And if any other PALS champions are present, I'm not able to track the Zoom participants list. So welcome to the PALS champions and the members from the Program Management Office of PALS. Now, the session is not new to the people who have been attending the program for very many years. So what format we have is we will not allow the participants to unmute. So most of you would have figured out by now that the mute option is not working. Mute or unmute option is not working. So what we will do is we will go on the listening mode, but that doesn't restrict you from interacting. Chat box is open. So meaningfully chat, talk regarding the session, ask questions regarding the session. We are here to monitor your questions, and we will, take it, post it to the professor, the speaker, and get them answered for you. There will be a separate Q&A session, and during that, we will try to moderate the questions. As you can raise hand, we will try to moderate, or we will let you unmute and then ask your questions also, depending upon the interest that is coming at that point in time. So there will be a registration link, there will be an attendance link that will be posted, and a feedback link finally after the session. Ensure that you mark your attendance and you also give a feedback for the session. And then, look out for a quiz during the session. It may come as a surprise at any time, and there will be a post-session quiz also. So with this, I invite Ms. Anuradha Ramanujam to, give a brief overview on PALS and invite the professor also as well. Over to you, Anu.
I'll make it as quick as possible to give as much time to Professor. PALS is an initiative of IIT alumni, all IIT alumni, which provides interventions in the form of webinars, workshops, and competitions to students, faculty, and management of engineering institutions around us. It was started way back in 2012 with 6 institutes in its kitty. Right now, last year we were 45, and we are aiming to expand our footprint all over South India. Earlier we were only in Chennai, then moved out of Chennai to rest of Tamil Nadu, and then during COVID to Andhra and Telangana, followed by Kerala and Karnataka this year in a big way. We also have our partner institute in Kathmandu Engineering College, and there are participants from there also attending this. We are extremely honored to have Dr. Srinivas Boppu, who is an assistant professor in the School of Electrical and Computer Sciences within the Department of Electronics and Communication, Indian Institute of Technology, Bhubaneswar. His research interests encompass high-level synthesis, programmable hardware accelerators, coarse-grained reconfigurable architectures, system-on-chip design, low-power VLSI, and CAD for VLSI. Dr. Boppu earned his PhD in hardware-software co-design from the University of Erlangen, Nuremberg, Germany in 2015, and holds an MSc in IC design from the NTU Singapore and TU Munich, Germany. Extremely happy to have you, sir, and look forward to your great session today. Students, yeah, you can go. You can take the floor.
Okay, ma'am. Yeah, thank you. Yeah, good. So, ma'am, you're able to see the screen, right?
Yes, sir.
Yes, sir.
The desktop
Okay,
screen is shown, and yes, the PPT is shown now.
okay, good. Yeah. So thanks a lot for the nice introduction, ma'am. Okay. So just the best would be that I'm just like you, maybe 20 years back. So that's the best introduction of myself. Okay. So aspiring to be a kind of electronics engineer. Good. So now, so today, so like as the title says, so we'll try to kind of talk about Verilog. How do we do some kind of a circuit design? Yeah. So kind of so few learning objectives for this kind of one and a half hour session would be, I just briefly talk about the Verilog itself, the blogging, and there are like typical questions, right? Whenever you attend an interview, this is the first question which we everybody asks. So the blocking statement and non-blocking, and then something called so what is the difference between latches, flip-flops, how do we model this finite state machine, and more on this will also talk about inferring latches and flip-flops. And then we can again talk about, so how do we really kind of this synthesize or maybe write codes which uses latches with flip-flops, or and with the preset pins, clear pins, or maybe or maybe the latches with preset pin, clear pins, or without them also we'll talk about. So just to give you kind of the set the stage right. So this lecture is not about of course it's a 1.5 hour is really kind of a short to really talk about the Verilog and talk about the syntax details and each modeling each type of circuits and all, right? So but what I'll try to really do is that there is a kind of a phobia among the students and even some of us as a faculty that okay, I mean designing with kind of a Verilog is really maybe not easy like C and all. Okay, so what we'll try to do in this lecture is that, so maybe I would say the last half an hour of the lecture, you will see the kind of the main content of the lecture where you will really feel that, I mean, if you know a simple Karnaugh map, yeah, so simple digital design basics, maybe coming up with given a truth table, we need to come up with some expression, or maybe use k-maps to really derive the kind of a circuit. If you know again those principles, and even we can really write the Verilog code, and not only write the Verilog code, but we can really visualize the circuit. Okay, so that's what I'm going to really show in the the last half an hour. And as I said, I mean, don't kind of expect that we'll talk about each aspect of the syntax and all those details. But again, as I said, right, so this is a kind of a semester long course we kind of teach at IIT Bhubaneswar. Okay, but again I'm just trying to pick the highlights from those lectures, and then wanted to present concisely so that everybody is motivated towards the digital design. And see how it is easy, and we just need to know only simple the Boolean kind of arithmetic. So without further ado, let's get into the topic. So now in this slide, what I'm trying to really show that maybe if you look at the evolution of these integrated circuits. So in the past we have these vacuum tubes. So that time also we are able to kind of build the computers, and we have even the discrete transistor era also. Okay, so even we are able to build the computers even that time. But of course, if you look at the size, right, maybe they're taking almost the size of a room. But then soon the companies started so when this integrated circuit era really started, so the integrated circuit means not only the discrete components, right, so but also the the connections, we are going to realize everything on a single piece of silicon. So it's everything is integrated. So that's where this integrated area, circuit era started. And then the companies like Apollo, Xerox, Apple, right, they soon started building the computers. And of course, right, everyone knows that Intel took the lead. And then they started building the Pentium 1, 2, 3, 4 and all. Yeah. And again, so if you look at right the kind of evolution, so the number of transistors which we are going to integrate on a single piece of silicon, right, so double, or maybe for every 18 months or 2 years. So as per the Moore's law. Okay, so that means if you have more transistors, that means you can think of more gates. If you have more gates, I mean we can do, let's say, much more tasks, right? So now the problem here is that, so if you ask ourselves that okay, even a simple full adder circuit, maybe we'll be able to kind of draw it on a paper, even even transistor level diagram. Imagine any kind of bigger level circuit. So again we won't be able to comprehend it on a single paper. So that's where actually, the complexity started really increasing. And then people started thinking about, so we also need some kind of a tools, yeah, that okay, for to handle such a bigger designs. So of course, what also happened is that okay, so this clock frequency started increasing, even the design complexity started also increasing. And then so people thought about okay, so like softwares, so we also need some kind of a languages to describe the hardware. And that's where the whole this electronic design and automation industry started. And so that's where the foundation for VHDL and Verilog and it started. So definitely, right, so today's circuits, it's all we cannot really comprehend on a single piece of paper. Okay, right. And then so definitely we need some kind of tools like Verilog, the languages like Verilog, to really describe any kind of state of the art designs. Okay, good. So here, so what is Verilog HDL, right? It's a kind of high-level language, so that can model, represent, and simulate the digital circuits. So it's a single language, right? So which can be used for even designing as well as kind of a testing. Okay, now, so one fundamental difference between your software languages and the Verilog is that, so the hardware is concurrent. So that means you have a parallel activity flow. That means, for instance, if you have a C program, right? So we have, let's say 10 statements. So one is executing, one after the other. So there's a kind of a sequence of statements. But now imagine you have a hardware. Let's assume that there are a lot of flip-flops in your design. So whenever, let's say for a passage of the clock comes, every kind of a flip-flop is trying to copy the D input to the Q, right? So that means there's a lot of parallel activity is happening. So that's where actually sometimes there's a difficulty if you're a software engineer and you wanted to really program in a hardware. So there might be a little bit difficulty, but it's kind of easy to understand the differences. Okay, good. So that's the main difference between a Verilog and a C language. There's a parallel or the concurrent a flow is there. And then so we also have, there are like different levels of abstraction. So like behavioral, data flow, and gate level modeling. In a single design, we can mix and all these designs. So if you look at the state of the art designs, any design, if you look at right, any company uses, right, for the legacy reasons, they have VHDL, Verilog, system Verilog, all kind of the languages you'll have any state of the art chips. Okay, so there are like a few which designed using Verilog, so it's listed here. So yeah, good. So now what is VHDL? VHDL is also kind of another language. So for again the digital system design. So mostly it is used in the European kind of countries. So but the Indian market is really mostly dominated by the Americans, right? So that's the reason in India and all, right. So definitely the Verilog is more popular than the VHDL. But in Europe and all, still the VHDL is really a popular still. Okay, now so what we do is that let's look at this simple design, the 4-bit triple carry counter. Okay, so again it's a triple carry counter, right? So basically, right, so as the name says, it's a triple carry means or asynchronous counter, right? So the Q output of one flip-flop is really connected to the clock of the next flip-flop, right? So this is a 4-bit counter. So again, right, so only the first flip-flop will get the clock, right? But the next flip-flop will get the clock from the previous the Q output. Okay, so that's what we have seen here. Okay, this is also shown here. Okay, now the question is, how do we really design this circuit? Okay, so now our objective is to really build the ripple carry counter. Okay, right? So there is a like bigger module. So let's assume that. So how we really kind of come up with this full let's say 4-bit ripple carry counter, let's say the design or architecture. So now let's assume that. So somehow we know how to build the T flip flops, right? So if you assume that, so once we have the T flip flops, exactly we have to connect these T flip flops as shown in the circuit. Okay, so now the question is, how do we really build this T flip flop? Okay, now so what is shown in this the down part is that, okay, so suppose if you know how to build a D flip flop, okay, by using D flip flop and an inverter we can build the T flip flop. Okay, so now only thing is that, so we of course, right, so we can really build the kind of inverter. So if you know how to really kind of build this D flip flop, okay, the T flip flop can be done, and then we can connect all this T flip flop in this fashion to kind of get the ripple carry counter. Okay, good. So now let's move forward. So this is stuck, it seems. Okay, good. So that's what is shown here. So ripple carry counter can be kind of built using 4 T flip flops. right? So TFF0 to TFF3, and each T flip-flop can be built using a D flip-flop and an inverter. So this you can think of as kind of a top-down flow, and you can also think of set hierarchical design. Yeah, good. So now, one of the main building block in Verilog is the module. So this is like if you have a kind of a bit of experience in C++, it's like your class definition. Okay, good. So now module is the kind of a basic building block in Verilog. So it could be an element or collection of lower level design blocks. So that means, so like class can have an objects of another class. So similarly, the class can be, of course, it's a kind of a singleton, or it can also instantiate another modules. So that's what I mean by this lower level design blocks. Okay, and then it communicates. Actually, basically the module communicates to the higher level box through its ports. So basically, it's interfaces. So again, it's the same analogy that okay. So we might have some kind of parameters for coming to the class. So similar. So we have this input and output ports. So by which uh, the module will communicate to its external world. So the best thing is that it hides the internal implementation details. That means as long as your inputs and outputs are really kind of not changing, it doesn't matter if there is a bug. You go and change the internal structure, right? Is it no? So we don't have to really kind of change the whole design and all. So that's the kind of the beauty of having the module definition. Okay. Good. So now, so for let's say to give you just kind of a skeleton of how the module will look like. So the module will have, it's kind of again a keyword. So there will be like an end module, and then we'll have this module name. It's kind of an identifier, and then so we'll have this module terminal list where so we will be kind of listing out input terminals and output terminals, and then so we'll be writing some part of the code. So declaring which is input and output, and maybe if needed, so we'll be instantiating other lower level modules. Okay, good. So now. So to give you an example, so we have this module T flip-flop. Okay, so it has these ports. Okay, Q, clock, reset. Okay, so that's what we have, the Q, clock, reset. Okay, and then so basically we have to describe the functionality of this module in this let's say kind of a lines. Okay, so that's right now we showed as like a showed as a dotted lines. Okay, good. So now the question is, how do we really kind of build this module? Okay, so as we just mentioned in Verilog, so we have different, let's say, abstraction levels. Okay, so we have this behavioral algorithmic level modeling. So that is kind of most commonly used, and then something called data flow level modeling, and there's something called gate level and the switch level. Okay, so then one idea is that so it's the same analogy with respect to your high level languages and then assembly level languages and low level languages, right? So the advantage of high level language is that they're like English like languages, right? Maybe they're portable across machines. Okay, but now if you write something in assembly language, what will happen is that okay, I mean they're not really portable. Okay, and again low level language, right? It's really difficult to even understand. So similarly, if you look at the switch level, right, or maybe the gate level, right? So you are trying to really specify how even the circuit is really going to be implemented, right? So but if you go to the data flow level or the behavior level modeling, right? So our synthesis tools have kind of a lot of flexibility in kind of kind of optimizing the circuit. So in general, so maybe as if you are a kind of second year student or a third year student, yeah, so definitely when the digital design is taught in the class, so we always introduce the student to the gate level, because they might be working with AND gate, OR gates, XOR gates. So it's easy to kind of model even at that level. But so any kind of higher level and a master level and all, so we always kind of ask the students to really model their designs using only the data flow or the behavioral model. Okay, so in industry, right, so there is also a term called RTL, register transfer level modeling. So basically the RTL stands for your VHDL or Verilog code. So now when it comes to the Verilog, so basically we are referring to the Verilog code which is written either mostly in data flow or behavioral modeling. So these two we can also call it as RTL or RTL modeling. Okay, good. So now just to give you kind of basic idea about the behavioral modeling. So in this example, what we are trying to really see that kind of a code for 2 by 1 mux. Okay, and then we have this like a list of ports here. Okay, And then, so for each list of ports, of course, we have to really specify, whether it's output or input. Yeah, right. So here, out is an output port. Again, the output is in a keyword, and input is a, of course, we have I0, I1. So those are like a two input signal, and so we have this select signal. Okay, good. So now, when it comes to the Verilog, so I mean, people always confuse. There are too many data types and all, but there are only two primary data types, which is called as net or wire. Both are same, and then there is something called reg. Okay, good. So now if you look at here, right, so when we declare these inputs, right, we never mentioned anything like, so it's an input net or input wire. By default, this I0 and I1 are kind of a net type. Okay, for the output, so now here, so right, so we are mentioning as a reg type. Okay, so there is always a confusion. So when we say it's a reg, maybe we'll think that it's a registered data type. That's fine, but so this is not same as the register which we always refer to in digital design. In a digital design, right, so whenever we say it's a register, maybe we are referring to maybe a flip-flop. But so here when we say it's a register, it's not really a flip-flop. At the end, it might result in a flip-flop, which kind of the same as your digital design, but it not necessarily that this register will always be synthesized as a flip-flop. Okay, now if you look at this mux, right, so multiplexer. Okay, it's a simple combinational design, right. So we'll also see an example later. Okay, right. So where we will get a kind of a flip-flop and all. But so do not confuse your register in digital design with maybe this register. Sometimes this register will definitely synthesize as the register which is a flip-flop, but it's not always. Okay, good. I made my point, I guess. Okay, now in Verilog, if you see, right, there's only one always block. Any kind of code, if you look at, right, whether it's a combinational or the sequential, there's only one, let's say, kind of procedure block, I would say. It's always block. Okay, so which is kind of a synthesizable, and we have initial block, so that mostly we will use in kind of writing test benches. Okay, here, so when you have this always block, so we have this at the rate symbol, and we have some kind of a sensitivity list. Okay, so we have this select line. Okay, so I0 and I1, right? So here, what is this means is that it's a sensitivity list. If any change happens in these, let's say, lines, or maybe on the signals, this whole blocks get triggered. Now, in a kind of few minutes back we said, so Verilog is a kind of a concurrent or a parallel level language, right? So here, suppose we in this, let's say, code, we have only one always block. But right, so if it's a bigger designs, we can have multiple always blocks, and each always block is executing in parallel. So that's where actually the parallelism or maybe the concurrency comes into picture. Okay, good. So now, so what we are saying here is that, okay, if S or I0 or I1 changes, you look at, so the S value. Okay, of course there is a case statement. Okay, we call this a case expression, and we have these case items. Okay, S could be value could be 0, or S value could be 1, right? So here in Verilog, so when somebody writes something like this, right, so what does it mean is that, so whatever follows after this, right, okay, D stands for decimal, and this is a number 0. Okay, suppose if I write 2 let's say D 0, what should I do is that, okay, whatever follows this D is a decimal number, I have to really represent with 2 bits. So in this case here, so the number of bits is really kind of mentioned or maybe specified by this number. So here 0 should be represented as 00, because so we have a 2 here. In this case, okay, so the 0 is there, but I have to represent only with single bit. Okay, so that means it's a single 0, 1 by 0. So we can also look at, so suppose somebody said 4-bit H, let's say 2. Okay, so that means, so whatever follows this number is a kind of hex number, and we have to represent with 4 bits, right? So it's a so 0 0 1 0. Okay, so in this case we have this one ticked 0. It exactly means it's a if value is 0. Okay, if it is 0, we have to choose I0, and if its value is 1, it's I1. So basically what comes out of this is that simple multiplexer where you have S, I0, I1, right? If this, right, so this I0 will be, of course, I should write here. So this should be 0 input, this is a 1 input, so this is I1. Okay, and this is my output out. Okay, so now I want, let's say, kind of maybe so whenever we teach into the higher, let's say, kind of graduate students, so they should really look at as a kind of a circuit. So whenever they kind of write a Verilog code, so instantaneously, right, so they should really look at how it's going to be synthesized. So that's what I want kind of even my faculty friends who are attending this session, that okay, so it's not about simulating the circuit. Okay, it's all about what comes, okay, after writing the code. So that really matters, and that's where actually we can really avoid maybe the simulation and synthesis mismatches. Okay, good. So let's move on. Okay, so here, so we talked about the behavioral modeling, and then in a data flow modeling, right? So now you can think of in a behavioral modeling, there's always a kind of an always block. So when it comes to the data flow, right, so we'll have what is this kind of a keyword called assign. So here the same thing we are saying, it's a multiplexer, but we are modeling in a different way using a data flow model. We're saying here, now if you look at here, so earlier circuit, whenever we declare this out, right, so we mentioned as a reg out. Okay, but in this case, so we will not mention. Okay, so here the assign expect that, okay, so its target, right, so on this left hand side we always a wire, but in the previous code, whenever we have an always, the left hand side signal should be kind of a register. Okay, so here I will like to tell you that, okay, there is a difference between these two blocks. Okay, so we call that always block as a procedural block. Okay, I'll go back here. So what I mean by procedural block, okay, so now in a procedural block, whatever we have in the left hand side, right, that should be a register. So now the register means here is that it's not really kind of a register of your digital design. It means that suppose if there is any change in these signals, okay, you evaluate the block and then maybe you update the value of out. But now what happens if this is not changing, right? Okay, so that's actually we have a notion called we have to save. Okay, that means the procedural blocks, so we have this left hand side, right? The left hand side will not always, let's say, drive the right hand side. Whenever there is a change, this value will get updated, and then after that it has to be saved. That is the reason, so we have to use the kind of a keyword called reg. Yeah, but whereas in a kind of an assign, let's say in the data flow model, so we always use this continuous assign. Okay, so here this is continuously evaluated, and then it's kind of a driving here. So that's the reason we just use a wire, and as I said, if you don't declare anything, so output out, right, it's a by default it's a wire. Okay, so here see, you might have seen this kind of expression, right? It's a conditional expression. If s equal to true, so we'll take this value, and if it's false, we'll take this value. Again, no, it's something like this, right? S, so it could be true, it could be false. If it's false, S0, it's a true, it's I1. So this is our out. Okay, good. So similarly, so the same multiplexer, right? So we can also really use kind of a gate level modeling, right? So what we can really say, so what is the multiplex expression if you wanted to write? Okay, of course I'm writing out, but my output is out. Yeah, so S bar, let's say I0 plus S into I1. Okay, so now how do I really get this S into I0? I should really use an AND gate, right? Okay, good. So let's say, so this is my I0, right? And of course this is my S into, let's say, I1. Okay, so now what I should do is that, okay, this is my S into I1. So now, right, I should use a bar. So this is my S bar into I0, and then I should really combine. Okay, so now to make this circuit, what I'm trying to really do is that here there's an AND gate, right? So what I'm trying to do is that I'm trying to instantiate an AND gate. Okay, so you can think of all the basic gates are available in the Verilog. So I'm just trying to instantiate an AND gate. Okay, so one of the input is this I'm calling it the SN. Okay, and then Sn is the input and I0 is input. Sn is one input and I0 is one input. And now we have this output y0. Okay, now when we are, let's say, writing using this primitive gates, so the first, let's say, thing which you write here is always an output port, and then we can have, let's say, two inputs or three inputs, then it will model as a two input gates or three input gates, or even we can have, let's say, n number, so that will model as a n input AND gate, but so only there is one output. Okay, similarly, so if I call this as a y1, so that output is y1 here, and one of the input is I1, and this is S input. Okay, so now how do I really get this Sn? So I instantiated a NOT gate, so I'm giving a S as an input, I'm getting this Sn as output. Okay, now this is my y0, that's what we have here, y0 y1, and this is my output, right? Okay, so now I'm instantiating an OR gate here. Okay, OR gate, so output is connected to this out signal, so y0 and y1. Okay, now you see, right? So what we have is that, okay, so I mean, if you're a second year student, right? So that's what we teach in the classes, right? So there is a one-to-one correspondence between what they learn and what they're going to really model as a in the Verilog, right? So maybe at a secondary level, so maybe this kind of a gate level modeling is useful. But now, for instance, let's say I'm trying to really synthesize this design using a kind of an ASIC library. So now what I'm trying to really do is that even though in my library I have a optimized multiplexer available to input multiplexer, okay, the MES and I0 and I1. This circuit is already available for me, but now what I'm trying to do that, tell the tool that, so please use one AND gate, another AND gate, an inverter and OR gate to really synthesize it. Okay, now this whole circuit might not be optimized compared to this one, which we already have it. Okay, so that is the reason, right? So when we go from the behavior level to the data flow and then you come to the structure level, right? We lose that flexibility. Okay, so that is the reason. I mean, as a kind of very initial user, it's okay to use even structural modeling. Yeah, but we always really recommend to use either data flow or the behavioral modeling, so that if your library has some optimized circuits, they get used in your actual synthesis. But again to teach the students at the second year, I think it's the best option we have. So similarly, so I'll not go into much details here. So the switch level, we seldom use it. So what we have is a transmission gate here. Okay, we have PMOS and NMOS. And now if you look at here, this S bar, right? So here, so whenever you have this CMOS, so we'll, if you instantiate this CMOS, we'll get one transmission gate here. So first one is always your output, and then the second one is your input. So right, so this is your out, and this is your input. And then we should really mention what is connected to the, let's say, your NMOS transistor, and then what is connected to your PMOS. So here, S bar is connected to the NMOS, and the P, let's say, S is connected to the P, right? So that's what we mentioned. So for if you look at maybe this gate, so right, so what is connected? So S is connected to N, and P is S bar is connected to P. Okay, good. So another input is I1 and out. But actually, right, this design, we seldom really use it. Okay, good. So now let's, we have a kind of a brief idea about, how do we really write the modules and all. Okay, as such, the module is not useful. So that is similar to your class. Okay, now we have a class definition, right? But it doesn't really kind of useful unless you create an object out of it. So similarly, this the same case here, right? So module is a kind of just a template from which actual objects are really made. Okay, maybe in a C++ we call this objects, but now we call them as let's say instances. And now if you look at here, right? So when you instantiate one module, each object will have its own kind of inputs, outputs, and other things. It's something similar to C++, right? Each object has its own kind of the what to say, the members and all. Okay, so each object has its own name, variables, and parameters and IO interface. Okay, so instantiation is nothing but the process of creating objects from a module template, and the objects are called instances. Okay, good. So now let's again go back to your ripple carry counter design. So this is what I'm going to really do. Okay, so I have this, let's say, module ripple carry counter. Okay, it takes the output is Q, and it takes the clock, and it's a reset. Okay, since it's a 4-bit counter, right? So now I have this, let's say, output Q. Okay, now so you see this notation, right? So 3 down to 0. Okay, so basically instead of writing Q0, Q1, Q2, Q3, right? So Verilog allows to really write what is known as kind of a vectors. Okay, so now here it means that the Q is a vector of 4 bits, and each one also can be accessed using this notation: Q0, Q1, and Q2, and Q3. Okay, something similar. Okay, so now so we have this inputs, clock and reset. Good. So now here what I'm trying to really do is that, as we mentioned, let's assume that somebody gave our T flip-flop module. Okay, what I'm trying to really do is that I'm trying to instantiate 4 times, and each time in an instantiation, right, I'm giving a different name: TFF0, 1, 2, 3. Right, that's what I did. Okay, and then so now I have to really connect them, right, as per the diagram which we have seen. Okay, if you remember what I said, so for the first, let's say, design itself, or the first flip-flop, we will give the clock. Okay, now let's assume that. Okay, so now we should really know how actually the T flip-flop will look like, right? So now let me show you how does the T flip-flop will look like. So this is that module T flip-flop. So the first port is your Q output, and the second port is your clock, and the third port is your reset. So now here, if you go back here, the original design, so now what happens is that, so this clock is connected to the clock of the T flip-flop. Okay, now you can think of, I can also really write something like this, clock CLK, okay, comma, reset, and then in bracket I can really reset. So here when I say this reset really corresponds to the T module, let's say port. So now that reset port is connected to the reset signal here, the clock, right, signal is connected to the clock port, and then so we had a Q is connected to Q of 0. Okay, good. So now we said for the second flip-flop onwards, right, the clock will be driven by the first flip-flop output. That means it should connect here, and this should be connected here, and this should be connected here. Yeah, but now you see, right, all the flip-flops will get the same reset signal. That's what we have. Okay, so sometimes what will happen is that, so many students will confuse, okay, what is this clock and this clock, right? So basically this clock is coming from your lower level module. Yeah, but now this clock is really different from this clock. So this CLK is the clock in this, let's say, module, but this CLK is the port of your T flip-flop. Okay, so once you do, kind of 1 or 2 designs, I think, no, you'll be able to understand. Okay, now let's go to the T flip-flop. So again, right, so we also have this module T flip-flop. Its output Q, clock, output is Q, inputs are clock and reset. Okay, that's how we declared here. Okay, good. Now, as I said, so somebody already gave us in the D flip-flop. Okay, so then what we said, by using the D flip-flop, we will connect. Okay, so whatever the D flip-flop, right? So I'm instantiating the D flip-flop with the name, DF0, right? So I think, its output is Q, input is D, yeah, and another inputs are, clock and reset. So basically, right, so output of, let's say, the Q is really connected. If you see here, what is happening? So there is a NOT gate, which we are calling N1. So whose input is Q and output is D, right? Again, this output D, right, is connected to this input. So that means you can think of that, okay, this is a Q, right? So it's connected, okay, this is a Q, right? So it's an inverter, it's connected to the D input. Okay, so this is how, we can really build the T flip-flop using a D flip-flop. That is what, it's really shown here. Okay, so nothing much. Okay, now, as I said, so, but how about the D flip-flop? Okay, now this is where, I can really use maybe my data flow modeling technique or maybe the behavioral modeling technique to really model the D flip-flop. So here again, so maybe later on also we'll see the few important things. Okay, right? So this is a block which is of interest to us, and this is a kind of a typical structure. So if you look at here, so we have this always passage reset, and so we have a negate of a clock. So now if I ask, right, so always there is a question whether it's a asynchronous reset or kind of a synchronous reset. So many of the students are getting confused. Now if you look at the block, right, so if I ask, right, when this block will be triggered, right, so I should look at the sensitivity list. Okay, now so if you look at the sensitivity list, so what we have the passage of reset or the negate of the clock. That means this block will be triggered, right, even though the passage of the reset comes, right? So there is no clock relation. So that means this block is nothing but maybe asynchronous reset, right? So now if it is a passage of reset, we are saying if it is a reset equal to 1, so we are the Q output should be 0, right? Else, right, of course Q equal to D, let's say D. Okay, now so some interesting question. So one of the student asked me, so we have something like this. We have so passage A, okay, or negate B. Okay, so we have something if let's say A Q equal to 1 take B 0, right? Else, right, so we have Q equal to let's say D. Now in this case, so what is the clock? So now most of the times, right, as a designers when we're doing, right, so we always use the meaningful names, right, the reset and clock. So now it so happens that this is kind of a consumption or the misinterpretation among the students that okay, so since this is a clock, this is going to be synthesized kind of a D flip-flop with a clock as the clock input. Okay, good. So now so there's one question, right, about there's async or sync, right? So now I'm asking myself this question that if we have this always block, right, when does this always block get triggered, right? So we have this passage reset or the negate clock. So when we have this R, right, what does it mean, right? Either this could happen or this could happen, right? So now let's assume that there is a passage of reset, right? This whole code will execute. So now that time, are you checking whether you have a negative of the clock or not? You're not checking, right? That means even this blocks is getting executed if the passage of the reset is coming. That's how I'm saying it's a, it's a asynchronous reset. Okay, good. So now, so the other point which I was trying to explain is that, so now here we have this passage A and negates, let's say B, right? So now if A we have something, else we have something. So in this, let's say two signals, which is a clock. So here maybe it's easy to really find out. So since I wrote this clock, maybe generally we write CLK or CLOCK, that will be the clock. Okay, it's not like that. Okay, now if you look at maybe the way we write now, if by looking at this A or B, right, we cannot say that A is a clock or B is a clock. So we have to understand actually how the Verilog does. Okay, so now again, if you look at this circuit, right, so this circuit, I mean this block will be triggered either when A changes or let's say B changes or in the passage of those. Okay, now since we are checking if A, right, that is going to be your asynchronous pin. So that means the A is going to be reset. So now we have something called else, right? So else means, right, of course, now else of what? Okay, so then negates B. So this statement is going to be executed as negates B. So that means what you can really expect is that, okay, there's a D, there's a Q, and now is a flip-flop, right? So I should connect the clock. So here we'll have a B, of course, since it's a negate, so we'll have a bubble here. Okay, and now there's a passage, right? So there's a passage. Okay, let's say if this is your reset pin, let's say R. Okay, this should be connected to your A. Good. So now, so maybe I'll just since somebody asked a question. Okay, so maybe I think I'll just clarify, one more point here. Right. Good. So now, let's say I have something like this. I think it's better to clarify this point. Okay. We have
a question on repeat how we are saying whether it is sync or async.
Yeah, I'm just coming to that. Okay. Okay. So now, okay. So now, if you look at this, let's say block. Okay. So earlier, what I wrote, always at the rate. I'm not sure if I zoom out, it's visible or not. So we have this passage reset, or let's say negates clock, doesn't matter. So negates clock we had. Okay, and then we have if reset. So right, so Q equal to 1 tick B0, else we have Q equal to D. Right, now if you look at, right, so this I'm going to really say that it's a asynchronous. The reason I say it's asynchronous because if you look at this, let's say always the sensitivity list, right? So that block will be triggered, either reset comes or the clock comes. So what actually the asynchronous means for the reset? Irrespective of the clock, your Q should change, right? So that will happen only here, right? So that is the reason we say it's asynchronous. Okay, so if you wanted to state me as a kind of in a rule, so whenever you have this passage of the reset or the negatives of the reset in your sensitivity list, that is going to be asynchronous, let's say reset. Now if you look at maybe this part of the code, we have this always passage of the clock. There's nothing like we have a reset or anything. That means whatever is going to be executed in this one, it has to be with respect to the clock. Whenever the passage of the clock comes, we have to check what. So here in this case, whenever the passage of the clock comes, okay, now you have to look at what is the reset value, whether it's a 0 or 1 or right. So that means indirectly what you're trying to say that you are going to sample your reset, okay, signal at the passage of the clock. What is this? It's a synchronous reset. Okay, now if you wanted to really have a synchronous reset, if you wanted to state me in terms of the rule, you should not have any reset or anything like that here. Okay, so you should only have the passage of the clock, and then whatever the reset or the set signal, everything will be synchronous. But now when you have this, the passage of reset or maybe passage of the set, right, in the always statement, those are going to be synthesized as your kind of asynchronous, let's say reset and set signal. So we'll also again talk about that later again. So as I said, last 30 minutes, you just wait for that. Okay, good. So now let's say we design the circuit. Okay, now how should we really let's say, kind of simulate it. Okay, we have to really write a test bench, right? Okay, so that's what we are going to really do that. Okay, but before trying to do that, so we understand what is known as a port connection rules. So here any design, right? So right, we'll call it as a DUT or whatever. Okay, so we'll keep the separate, and the test bench will write it separately, right? In the test bench we will be using a lot of initial blocks and all those things which are not really synthesizable, right? So that's the reason always. So design will keep it in separate file, and the test bench will write in a separate file, and then the DUT will be instantiated in the let's say the kind of the test bench. So that's what we have here. Okay, now if you look at this stimulus code, what we're trying to really do is that the stimulus, right, as such, it doesn't take in inputs or anything from outside. That's the reason the port list is empty. Okay, now we instantiated our ripple carry counter. Okay, so ripple carry counter we instantiated, and then now we are saying, okay, this is my output and this is a clock and reset. Now in a test bench, what we need to do is that, so we have to provide, so we have to really provide, different kind of input stimuli, right? So maybe the clock signal, reset signal, yeah, and maybe you have to watch out the output. So to do that, so what we have is a register, clock, and a reset and a queue. Again, the question, why reg? So why, let's say, the wire for this, let's say, queue. Okay, so that's what actually it's really mentioned here. Okay, now we can think of any module has let's say two sides. One is internal to the module, and one is external to the module. So now if you look at, right, so this is our, let's say, ripple carry counter. Okay, all the inputs are actually the, let's say, nets, right? Now you wanted to really drive, right, some values onto it, right? Okay, now in the test bench, okay, if you look at here, what we are trying to really do, we're trying to really change the clock signal, right? Okay, now we have this initial block. In the beginning we are saying it's a clock equal to 1 tick B0. So what does it mean, right? So if say this is my time t equal to 0, in the beginning it is 0. Okay, we are saying that always at hash 5 clock equal to not clock. So you can think of this hash 5 as a kind of a delay. Okay, so that means if you say this is my time t equal to 0, after let's say 5 time units, okay, if it is 0, it has to be, let's say, 1, clock equal to not clock. Now the question is that at time t equal to 1, what is the clock value, right? Okay, now as I said, whenever we have this notion that, okay, we have to save the value until the next assignment happens, right? That means up to 0 to 5, right, until the next assignment happens. So the clock has to really save the value of 0. There's no question, so we have to use this data type called register, right? So now, I mean, this is kind of a rule you can think of whenever you're modeling. Okay, am I going to really drive this continuously? If yes, we will have a wire. Okay, no, we are going to kind of update it, some kind of at different times, the value. So we have to really declare with a clock. Okay, so now by using this clock and always statement, so we really create what is known as the clock here, right? So in the beginning it's a 1 tick B0, and this is like an always, right? Always means it has to execute until you stop your simulation. So not 5 clock, right? Hash 5, right? After 5 time units, clock equal to not clock again, right? So this is my 5 time unit. So now let's say this is my 10th time unit, right? So clock equal to 1, and it will be 0 again. Okay, again, so right at 15 time units, again it will be 1. So basically, right, so it's really generating the clock. Okay, good. So now if you look at, right, so we have this initial block. So we can have many initial blocks as well, but each initial block will start at time t equal to 0, and then it will execute only once during the simulation until you stop. Okay, good. So now you said it's in the beginning clock 1 tick B0, but now if you look at maybe this initial block, you are saying that so reset equal to 1 tick B1. Okay, so in the beginning reset equal to 1 tick B1. Okay, but now after 15 time units, you are saying that so reset equal to 0. Okay, if you look at our previous, let's say, the ripple carry counter, right? So it's a active high reset. That means as long as the reset is 1, right, so your output is always 0, but maybe at 15 you're releasing the, let's say, reset. So then maybe the counter should really increment. Okay, so then what you're trying to really do is that, of course, it's a it's a free running counter, right? So that means the counter value should really increase. Maybe it reaches up to 16, and then, or f value, and then it should reset itself, and then maybe continue with 0 again. Okay, but now we are saying that after 180, right? So now when you look at this 180, right, what you should see that from the starting time, it's a 15 plus 180, or maybe from the last event, it's a 180 signal. That means if you, let's say it's a 180 from the time t equal to 0, so 15 plus 180, total at 195. So again, you're trying to really reset the counter to, let's say 1. Okay, good. So now again, you are saying that maybe 195 plus 10. Okay, again, trying to really reset the 0. Again, the counter should continue. But when this reset equal to 1 again, so the counter should really reset to 0. And then we are saying that, so at $20, it's finished. That means 195 plus 10 plus 20 at this time. Oh, now you're saying that, okay, I'm done with the simulation. So please stop. We wanted to really stop the simulator. Okay, now, so we have this initial block, okay, by which we're, kind of monitoring the output waveforms, right? It's something you can think of. Now, it's like, your $printf to the screen, and it's printing the value in the, let's say, decimal format. Yeah, this kind of a format specifier. Okay, so that's what will happen. Okay, so these are a clock signal at exactly at t equal to 15. Yeah, so the reset was 0. So we have this, the counter really kind of, incremented, and it reaches up to 15, right? Of course, right? After 15, it should really continue, right? Again, 0, 1, 2, but this is at exactly 195. You made your reset equal to 1 again. So then the counter should really reset. And then at this point again, you release the reset value, and then again it start counting. So this is what happens. And now these things can be really seen in the GTK waveform later on. Okay, good. So now, so since we had this statement, right? So this monitor, this $time and output Q percentage D, right? So that's the reason it's also prints you to the screen these values. Okay, so I think it's kind of a pretty much similar. Okay, so now maybe if you look at this $finish, right, on this $monitor $time, right? So there are some kind of a tasks, system tasks available for you to kind of start the simulation, stop the simulation, or monitor the different values. Again, there's a kind of a whole one chapter really available in Bhaskar book. So if interested, somebody can really look at it. Okay, so now the interesting part would be, okay, so maybe I'll just maybe for the take of, it's, if you use, maybe for the sake of time, I will not show. So there are tools like Verilog and the GTK Wave. So there are two open source tools, right, which you can really install in Ubuntu. Okay, and then just compile this, all the Verilog files using, let's say this Icarus Verilog tool, and then so it will generate a file known as a VCD. Okay, good. And then so we can just open the waveforms. Okay, and then exactly see the kind of exactly whatever you are seeing these waveforms, that can be seen in the the in a textual form or in the kind of a the graphical form in the GTK wave. Okay, good. So okay, now the important stuff, like I think I just kind of build the basic background for to describe this blocking and the non-blocking statements. Okay, so there's always a question, if let's attend an interview, the first question, so do you know what is a blocking and non-blocking statement? Okay, now let's look at this example. Yeah, so here what we have is like again there's a one always block here and the second always block here. So what is the difference you see, right? Only in this assignments. Okay, in general, so with whatever we denote with kind of equal sign, these are the blocking statements, and then whatever we denote with so my screen is visible, ma'am?
Okay. Yes, sir. It is visible.
Okay, good. Yeah. So now whatever we denote with maybe the less than or equal, right? So it's going to be a non-blocking state. Okay, now if you look at this circuit, okay, so maybe I'll make a statement. Okay, so there are two statements here, right? Y equal to A and B, and let Z equal to B and C. Okay, so here, so again Y equal to A and B have, and V equal to B or C we have. Okay, so now if you look at these, let's say two circuits. Okay, so whether it's a blocking by using this kind of an equal symbols model or the less than or equal or non-blocking statements, you are going to get exactly the same, let's say same circuit, right? So Y is nothing but A and B, right? So Z is nothing but B and C. The reason is that, okay, so I'll explain with the next slides. Okay, so here, so again we have two different let's say codes. Okay, so here again this block will be executed whenever this ABC changes, or again here also the same block. Okay, the difference is that again we have a blocking here, we have a non-blocking here. So now if you look at, so we have this A XOR B, and here we have N1 XR C, right? So similarly, A XR B, here we have N1 XR C. Okay, good. So now when you synthesize this circuit, so there will be a difference between the blocking and non-blocking, right? But now if you look at the previous circuit, right, there is no difference. The reason is that, okay, now if you look at carefully, you're trying to really calculate something with, this A and B. Okay, so we got this left hand side Y, right? So this Y is never used in the right hand side. Okay, so we call this as signal interdependence. Okay, let's assume that, so there is no second statement, there is only first statement. So that means this is not there, this is not there. Whether it's a blocking, non-blocking, we get the same thing. But the problem only comes when, okay, if you look at here, right, we have more than one statement, but what is calculated is getting used in the next statement. Okay, but now if you look at the previous circuit, right, so here this Y is never used or Z is never used, right? So now when there is no signal interdependency, so what is the signal interdependency? So you calculate something that you use in the next statement. So you can think of whatever appears on the left hand side, that in the next statement it will appear on the right hand side. Okay, so that's what we have here. Now whenever you have such things, right, the blocking and non-blocking statement will differ. Okay, so here what is the difference? So right, so since the name says it's a blocking, right, so now, okay, now let's assume that, so what are the primary inputs? A and B, right? So that means somebody gives A and B, I will calculate N1. But now to calculate my S, I will always use the updated value of the, let's say, N1. That means whatever the calculated, it's a new value, this N1 value, I'm going to use it in the next statement. But now you can think of, so when it comes to this circuit, okay, so I use A and B to calculate the N1, right? Since it's not blocking, that means these two statements are executing in parallel. Now to calculate this, let's say S, at the same time when I'm calculating this A and B, there's no way I have to use its previous value, right? So that's what is also shown in the simulation. Okay, now here, if you look at this A and B, so N1, right? So it's XR operation, right? It's a 0, 0, it's a 0. So 0, 0, it's a 0, 0, 1, it's a 1. Okay, 0, 1, it's a 1, 1, 0, it's a 1, 1, 0, it's a 1, and 1, 1, 0. Now to calculate this S, right, in the blocking statement, as I said, I have to use the updated value of N1. Okay, now so this is my C, and then this 0, right? So 0 and 0, it's a 0, 1, 0, 1, 0, 1, it's a 1, 1, 1, it's a 0, 0, 1, it's a 1, 1, and okay, so this 1 again 0, so 0 and 0, it's a 0, 1 and 0, 0. Okay, so now you see, right? So to calculate this S, I'm using the latest value of N1, which is calculated here. So that means I can also really say that, so this statement is really blocked by this one. So that is the reason we call it as blocked. Now let's say blocking statements. But now if you look at maybe the second part, okay, so this N1 will be the same in both cases. But look at the S, right? What will happen is that now if you look at this S, right, let's look at the value which you are getting calculated here. I'll take the current value of C because it's the primary input, but I always take the previous value of 0, and that's N1, not the current value, right? 0 and 0, it's a 0. Okay, now to calculate this part, 1, and here it's a 1, right? It's a 0. Okay, again 0 and the previous value 1, it's a 1. It's a 1, okay, and the previous value is 1, it's a 0. This is 0 and this is a 1. Okay, I'll take this 1. It's a 1, 0, it's a 1. Now you see the difference, right? Okay, so what we'll do is that means this statement is not blocked by this one, right? Both are executing in parallel. So now since I have N1 here, what value of N1 I should use? Okay, the question is, the answer is you have to use the previous value of N1. Okay, now as I said, whenever you have this signal dependency or signal interdependency, right, that means so something you calculate on the left hand side that will appear on the right hand side. So that's where these kind of a circuits will really differ. Okay, good. So now again just look at one more simple example. So we have this always passage of the clock. So now you can think of as a rule, whenever you have a passage of the clock, whatever this left hand side variable, right, they should really appear as your the flip-flops. Okay, good. So now this B and F should be really going to be kind of a synthesizer flip-flop. Okay, so similarly again here we have a passage of the clock, B and F are going to be synthesized as flip-flop. Okay, good. Now the question is, so we have signal dependency, right? So here also we have signal dependency. But now the beauty is that this statement is not blocked by this one. That means they are executing in parallel at the same time. But now, so here, that means we have to read the value of A and store it in B. But again, the updated value of B we have to take. What does it mean? It's same as saying that we should really take A value, right? So now once you do the synthesis, right, what exactly we'll get is that this is our, let's say, B and these are F, right? You see, right, B also gets a value of A and F also will get the value of A. But now if you look at the other one, okay, so B will get the value of A. Yeah, so B, right? So B will get a value of A, okay, but right, F will get a value of previous value of B, right? So that means you see, right? So this F will get a previous value of B. Now you see, right? So this is going to be kind of, the parallel architecture, but no, this is more of a, kind of a, delayed by one cycle. Okay, good. So with these two examples, I think, you can correlate. So what is going to happen? So whenever we have this kind of a signal dependencies or this inter-signal dependencies, both circuits are really going to be differing in what they come out. So this is one of kind of one fundamental question, everyone asks. Okay. So here, I mean, whatever we are trying to explain in a kind of a pictorially or here, so just we are trying to explain using the waveform. So once the slides are, given to you, so maybe you can have a look at it. Okay, good. So now there is also kind of, one rule which we would follow that, okay, whenever we are modeling in a combination logic, always use the blocking, right? So whenever you're using, kind of a sequential logic, use non-blocking statements. Okay, good, fine. Okay, now, so, okay, now let's again, so revisit. So there is always, kind of a question, when do I get a latch and when do I get a flip-flop? Okay, so in the next set of slides, we are trying to really see what exactly the difference between a latch and a flip-flop, and what kind of a code we should really write to infer a latch, and how do we write a code to infer a flip-flop. Okay, here what is shown is that kind of a D latch. Okay, good. So now if you look at this code, right, so again, kind of a D latch, and we have a simple outputs and the inputs. But now if you look at, what is important is that always this, kind of a always block. So if you look at this code carefully, right, we are saying that, okay, if C changes or D changes, okay, good, C changes or D changes, and if C equal to 1, then you kind of, Q equal to D, and of course, right, the Q bar will be, right, so Q bar or Qn, it's the same, so it's a negate version. Okay, now if you look at this code, right, so what is happening is that, so this whole block will be executed whenever C changes or D changes. Okay, now whenever we ask about, maybe let me ask you in this following way. Okay, let's talk about the D flip-flop. What is important is that that's D input, Q input, and the enable input. Okay, good. Now the question is, what should I really connect it to this D? What should I really connect it to this Q, and what should I really connect this to input? Here, let's say enable input. So now in this code, okay, so we have this capital C and capital D, right? Okay, now out of these, let's say 2 pins, so which one I should really connect it to, this D pin, or which one I should connect it to the enable pin? I know I'm just saying that, okay, this is going to be synthesized as a latch. Okay, now if you look at the carefully the code, so actually, right, by looking at the code, we should be really able to kind of, tell that, okay, this is going to be, connected to the, let's say, enable pin, and this is going to be connected to the D pin. So now if you see, right, so this block get triggered when C changes or D changes, right? Now you can think of, the latch behavior, right? Right. So enable could be always 1, but D changes, right? The Q should also really change, right? It's not necessary that, okay, enable is only changed, then the Q should update. No, as long as the enable equal to 1, for instance, if the D changes multiple times, the Q should also change. So that is the reason we always have C or D. Okay, right? Okay, now if C equal to 1, we are saying, okay, now if the C equal to 1 means maybe it's something like, if you're saying enable, if it's a kind of enable or enable equal to true, then only you change, else you just save it. So then, so this enable pin is going to be connected to C, and then this is connected to D, and of course, right, so here our output is also Q. It's a Q. Okay, good. So now one thing you need to remember is that, maybe I'll tell you that after discussing the flop. Okay, now when you come to the flip, let's say flip flop. So now again, if you wanted to infer a flip flop, always you should have something like this. Either it could be pass edge or it could be neg edge. Now, in the previous code, since there is no pass edge, I can really tell you that there is no flip-flop of question of realizing a flip-flop. It could be a latch or something else, but there's no question of flip-flop. But now once you have this pass edge or a neg edge, right, all this were left-hand side variable, right, had to be synthesized as a kind of a flip-flop. Okay, now if you look at here, this pass edge clock, that's all. So the Q will be your the flip-flop. It's a DQ. Let's say now this clock. Okay, now what is connected to this clock pin? So the CLO, CK signal will be connected. And then what is the D input? Okay, D input is connected to maybe this small d. Okay, and of course, so we have this capital Q, it will be connected to capital Q. That's all. Okay, now we can also have, as I said, right? So this is what the discussion we have, this asynchronous reset, right? So now if you look at this block, so this block is executed either pass edge of the clock or the neg edge of a reset, right? So that is the reason what we have here, right? So now since this is it's mentioned in the sensitivity list, this is going to be an asynchronous reset, and of course it will check whether it's a not reset, it's a 0, else it's a D. Okay, so similarly we can also have, so here we have neg edge reset we have, and neg edge preset we have. Okay, that means we can also have a set and reset pins, right? Okay, that's what we have. So now both are going to be asynchronous. Okay, so now it's not reset, so it's a 0. If the reset pins, like it's an active low pin here. Okay, and now it's an active low set as well, right? If the preset pin is let's say low, we'll set the output to 1, and else we have let's say Q. I mean the output. Okay, now so there's an interesting question here. Okay, so maybe I'll again switch back to this slide. So we have something like this, always at the rate. So pass edge A, we have pass edge B, we have pass edge C. Okay, now if then I'll have if A, let's say Q equal to 1 tick B0, else if it's a B, Q equal to 1 tick B1. Okay, else I will say my Q equals to D. Okay, so now if someone asks, so what is a reset pin? What is a set pin? What is a clock pin? How do we answer? So earlier circuit, right? So since we wrote something like a reset name and a set name and a clock, and we are saying that okay, reset may be reset pin, and maybe the set may be the set pin, and the positive the negative of the clock we wrote, and then the signal name was CLK. That is the reason it's a clock. No. So if you look at here, so what we have this passage A and a passage B and a passage C, right? I have to look at the code. So now if say if A is mentioned, right? That means if you checking something, if A means it has a higher priority, you're checking on this pin. Okay. So if A, that means it's a 1 tick B0. Oh, now you can think of since you are setting the Q to 0, that A could be your reset equivalent. Now then you are having else if, right? So out of this reset and set, which has a higher priority? Reset. If the reset is not active, you check the next pin B, and you are setting the output to 1. Oh, now you can think of this B as maybe kind of a set pin. Okay, now you have something called else. So this statement will execute, right? When these two are not there, right? When it will execute? The passage of the C. That means when you draw the flip-flop, so now when you're drawing the clock, so right? So this clock pin should be connected to C. Okay, of course, this D pin, Q pin. And let's say you have a reset pin. So this should be connected to A, right? And you have the set pin. Let's say it should be connected to B. Okay, so now in the previous, let's say this circuit, so since this is a reset, it's a reset, or since this is mentioned as a preset, it's a preset signal. That's not true. So we have to really look at the code. I hope I made my point clear. Okay, good. So let's move on. Okay, Ian, so we can also have a flip-flop with the enable pin. So we have again a not reset and not preset, and we are checking else if enable, right? Of course, this statement is going to be executed when the passage of the clock there, but again the passage of the clock, you're checking the enable signal. What does it mean? It's going to be synchronous enable. Okay, now reset and preset are asynchronous, but now you're going to check enable with respect to the passage clock. That means this is going to be synthesized as a flip-flop with synchronous enable signal. Of course, we have a reset and set signal, but we also have an enable signal which is synchronous to the clock. Good. Fine. Okay. So now, so as I said, so just okay. Okay. Now there's a question, right? So when do I get a latch and when do I get a flip-flop? Okay, let's look at the simple code, what we have. Okay. So this is a simple ALU signal, let's kind of a block. So we have this control, a signal A and B are two inputs, Z is an output, right? So now if you look at this block, what we have, always at the rate, okay, right? And you're changing, I mean, if there is a change in any of these signals, okay, so this should be executed. Okay, now if you look at it, what we have, if control Z equal to A and B, else if Z equal to A or B. Now if you look at, this A and B signals are Z, right? They are in a kind of a big and in format. So instead of 1 0, we have 0 1, doesn't matter. Okay, now so here if control the Z is defined, else also Z is defined. Okay, now what is going to happen is that if I synthesize this circuit, okay, so this is a control, okay, if the control equal to 1, right, okay, and the control could be 0, okay, now this Z0 is there, okay, right, if the control equal to 1, so what is going to happen is that, so we have an OR gate here, okay, so this is my A0 B0, so we'll have this is A0 B0. So if you see it, so control, right, so control is a 1, right, so we should AND, if the control equal to 0, we should AND. So since we have, okay, so right, so for instance, so for Z0 we have to synthesize, and the Z1 also will get exactly the same circuit. Okay, good. So now let's look at maybe this code. So what is happening here is that it's something similar. So again, so these are some inputs and outputs, but look at the always block. So now what we're trying to really do is that, so this always block will be executed when clock A or change in here. But now what we're trying to really do, if clock A, maybe you're trying to assign, but else what we have to do, right? So here, that's where, the notion of, the saving will come. If clock, maybe you're assigning, else indirectly you're saying that you have to kind of a store, right? Right? So that's where, the latch will come into picture. But if you look at maybe the other one, right? You're saying if do something, else also do something. That means, so Z is being assigned in if part as well as else part. That means I can also really specify that for all possible combinations of the control. Control could be 0 or 1, Z is specified. Then this is going to be a pure combination logic, right? So here if you look at, right, so there's nothing like, pass edge the clock or something where we can get a flip-flop. Okay, now since there's no pass edge of clock, there's no question of flip-flop. There could be a latch if it's incompletely specified. So if you look at the block, right, if clock A, the next state is mentioned, but if the clock is, let's say, 0, so indirectly you're saying that you have to store, and this is going to be synthesized as a latch. So that's what, kind of mentioned in this slide. Okay, so now, right, so you can think of the CK pin as an enable pin, right? So the enable pin is connected to, right, to clock A, right? So that's what we have. So all the enable pins are really connected to the clock, right? And then of course, right, the D pins are connected to, if it is next state 1, it's a 1 0 means 0, 2 is 2 connected. Okay, good. So now let's look at this code. It's something similar. So now since we have the passage of the clock, right, there's no question we'll get a flip-flop. The next state is going to be a flip-flop. Now the question is, if you think of a flip-flop, right? Okay, so let's say D, Q we have, and the clock pin, right? So now we have to really find out which is, which signals are get connected to what. Okay, so this clock is connected to clock. Okay, so the D input is connected to this current state. Okay, and the Q will be your next state. So since of course the current state and next state are 4-bit signals, right? So this structure can be really repeated 4 times as shown in the circuit, right? So for each, let's say, bit, we'll have 1 flip-flop, 4 flip. Okay, good. So now, so okay, now this is what I said, the last 15-20 minutes of the lecture. So I'll make sure that it's really exciting. Okay, good. Now this is somebody gives you a circuit. Okay, so by looking at the so far explanation, right, So since we have, at least a negate of the clock, we can expect what? Yeah. So the next state is going to be a flip-flop, right? So now we have some kind of, if reset something else, let's say not something, right? So basically, let's try to understand. So when we are talking about synthesis, or if of course, right, you wrote a kind of a Verilog code, what is our intention, right? Ultimately, this is going to be converted into some kind of a real circuit with the flip-flops, or maybe some kind of a combination logic, driving the D inputs and all those things, right? So that means, let's assume that it will synthesize as a flip-flops. Okay, so this flip-flop means, let's assume always a D flip-flop, D, let's say Q, and the clock pin. Okay, since it's a negate of the clock A, so we can also assume that A, so we have a bubble. Okay, now the question is, by whatever you write in this circuit, what we have to do is that we have to derive the logic for the D input, what the clock should be connected to, right? So since we have this reset and let's say set pins, right? Maybe in our library we have a flip-flop with a reset pins and a preset, let's say set pins. Okay, so let's say PD pins, CD pins, clear pins, or maybe set pins. We can use R or S names, doesn't matter. Okay, right? So now the question is, how do we really get this whole logic? Okay, so that's what I'm trying to really explain in the next 15 minutes. Okay, good. Now, so what I do is to save the time. So I already kind of had this written. Okay, you should be able to see my, let's say, notepad. Okay, so here what I did was the same code I wrote. Okay, so negate of reset, we have, or the negate of set, we have this negate of clock B. So we have, let's say, this part of the code. So now the question is, how do we synthesize the circuit using D flip-flops? Let's assume that in our library we have a D flip-flops with preset and clear pins. So what I mean by that is that, okay, now I have a, let's say, D flip-flop, which is D input, Q input. Okay, maybe CD corresponds to maybe the clear, and maybe this PD corresponds to maybe a set pin. Okay, now how do I really derive the logic for these things? Okay, now later on also we'll see that if you do not have this PD pin, CD pin, but I have only a flip-flop with D pin, what will happen? Okay, that's what we are going to see. Now what I'm trying to really do is that, so I'm just trying to come up with a simple truth table. Okay, so here what I have is that my input signals are set and reset, and the output is my next state, right? So since we have, let's say, 4 bits for the next state and the current state. Okay, so what I'm trying to do is that for each bit I'm trying to really do it differently. Okay, so we have this next state 0. Okay, let's try to synthesize the code for the next state 0. Okay, so according to our code, right, so what we have, if not reset, that means the reset should be 0. Then of course we don't check the set or maybe any other thing, right? So right, set could be x stands for, it could be 0 or 1, doesn't matter. I have to set my output to 0, right? So it's a 12, right? 12 means it's a 1100. Okay, suppose if the reset value is 1, okay, then I have to check if not set, right? Not set means it's a 0. I'm checking 0, then I should set my output to 1. Else, so now when both are 1 1, of course, right, I should assign based on the clock. So that means, so basically this condition, last 1 1 condition, is taken care by clock A. So now if I have a kind of a flip-flop, let's assume that I have a, let's say, flip-flop with a this negates, right? So negates, flip-flop I have. So simply what I have to do is that, what is my clock signal name? It's a clock A, right? I'm connecting it, clock A. Right. Now, so I have to really derive the logic for the PD pin, and I have to derive the logic for the CD pin. So now what is the guarantee that in my library I do have a, let's say, the flip-flop with the PD pin. I could also have a flip-flop with active low preset pin or active low CD pin. So now depending upon this, so we have to synthesize our logic. Okay, now if you look, let's assume that, so we have an active high pin PD. So now what does it mean? So whenever you apply a signal 1 here, the output should be set. So if you have a CD pin here, what does it mean? If you apply 1 here, the output should set to 0. Right, that's what the preset and set pin means, right? So similarly what we do here, okay, so where we are setting the output to 0, right? This point, right? That means this combination 0x combination should really drive my output to 0, right? Okay, now the 0x means what? Yeah, so now 0x, right? Okay, so okay, so 0x means what? So of course set I just kind of neglect, right? So only the reset, right? So that means it's a reset bar. Okay, now let's assume that. Okay, so that's what I shown here. I have a CD pin here, so maybe sorry, CD. So now if you see here, what is happening is that there's a reset. Okay, reset equal to 0. Let's assume value 0. I'll get a 1 here. So since this CD pin is active high, this 1 is connected here. It's active high. The output is set to 0. Okay, now so what is my PD logic? So if you look at this PD logic, right? Okay, now this is where this condition. So my output should be set to 1. Okay, now how do I get the condition? Sorry, so reset should be 1. Okay, and then it's a set bar. Okay, that's what I write. So I'm just ending it. Okay, it's a set bar, and then this is reset. Okay, I'm just connecting here. Okay, now you can think of, right? So this is a 1, and if I have 0, so this will be 1, 1, 1. So it's a, now of course you'll get a 1 here. The output is set to 1. Okay, now you see, right? So this D input will be effective only when either preset or set is not active, right? So then, right, of course, right? So maybe I forgot that. So I should also really have a clock signal here, right? This clock A or clock B. Okay, good. So now, similarly, if you try to do for the next state 1, okay. Now, if you look at the next state 1, so what is happening is that, so since both are zeros, right? Right. So 0x again, if you look at, right, so it's a not reset, right? It's a 0. This x also is a 0, and of course reset equal to 1, and the set equal to 0 also is 0. That means these two combinations are really driving the output to 0. Okay, now I mean, I can really save the kind of hardware by not using a kind of a flip flop with a both preset and set, let's say set pins. So in this case, so I know that in these two cases I will only drive the output to 0, right? So why should I really use a flip flop with maybe a bit expensive with a PD pin? So what I'll do is that I'll use only the flip flop with a CD pin. Okay, so now that's what I have here, right? Because it's driving the output to 0. Okay, now so how do I get the logic for these two conditions? Simply what I'm trying to do is that, okay, I'm trying to really, okay, now here, so we need to get a 1, right? So now that means what are the cases, right? It's a 0 0, right? 0 0 case and 0 1 case and 1 0, right? So it's a 1 0. So on the left side I have set and reset. So basically I'm just trying to group it. Okay, so now what is CD logic? So this one and this one, right? So two kind of terms we have, so set bar and reset bar. I'm just connecting the logic, right? Now again you see, right, it could happen that I do not have a flip flop with a active high CD pin, right? So now I have a flip flop with a active low CD pin. So then what I have to do is that instead of getting a 1 here, I should get a 0, right? Now if you look at this logic, right, what do you have? Either this should be 0 or this should be 0, right? So that's what we have, right? So now what will happen? See, right, let's assume that this is 0, this is 0, right? One of them is 0. What will happen? The output is 0. So CD equal to 0, right? Then output will be 0. This will not only work when you have both 1, we have a 1. Okay, that time the output should be really copied from the current state 1 to the next state 1. Okay, good. Similarly, if you look at this next state 2, right? Again, this part, right? So now we are talking about this bit 1 comma 1, right? Again, if you see, right, in both cases the output is being set to 1. Okay, now so why do I really use a flip flop with both pins? It's expensive, right? I will use only the flip flop with single PD pin. Okay, right? So PD pin. Yeah. So now how do you get the logic? The same thing now, right? So the same condition here, right? So set and reset. Let's say reset bar plus set bar. Okay. So now if you do not have, let's say again the active high PD pin, right? So if you have a let's say flip flop with the active low pin, so we should get a 0 here. Okay, so basically what you write, so once you get this PD logic, what you need to do is just need to invert it. Okay, you'll get this logic, right? So now in this fashion, what will happen is that the whole circuit will really get synthesized. Now if you look at here, okay, let's go back to the slides. Okay, right? So what we have here now, you see, right, these are simply the statements, right? So what we are trying to really do, right, we're trying to really convert this whole logic into some kind of a circuit, right? where, okay, what is a circuit? A circuit with the flip-flops. Okay, now immediately this question come to our mind. What should be connected to the clock? What should be connected to the D input? What should be connected to the preset input? What should be connected to the set input? Now, what actually the tool does is that what we have done with a simple example. So now in this case, these are, let's say, 12 and 5, the numbers, which we took it for, to make you kind of, feel easy. But instead of this 12 and 5, there might be some kind of a complicated logic. Again, right, this logic should come from somewhere, right? It's going to be some kind of a, combinational, let's say, logic, right? So now, so with this example, what I'm trying to really tell you that once we know some of these fundamentals, okay, when we get a flop or let's say latch, once we understood that, okay, now these questions we should ask ourselves. Okay, what is connected to, let's say, clock or enable pin? What will get connected to the D pin? What will be connected to the maybe enable, the set pins and reset pins? All answers are here, right? Now, if you look at here, right? So what we do? What did we do? So did we do any some kind of a complicated logic? No, right? Simply what we wrote is a simple truth table, nothing else. And then we're trying to really derive the logic for each of these pins, right? So believe me, that's what actually all the synthesis tool does, even for any complicated logic. Okay, in a nutshell. Okay, good. Now, so let's go back. Okay, so here, so I think there's one more important thing which I think I wanted to highlight. Now, so far what we talked about, so we have, let's say, the flip-flops with preset pins and the, let's say, reset, let's say, or maybe the set pins or any one of them. But let's assume that I do not have a library, okay, which has these, let's say, reset and set pins, but I have only a simple D flip-flop. So how does the logic will get synthesized, right? Again, what the tool does is very simple. So since it's asynchronous input, right, or asynchronous set and reset, right, now we can think of, right? So what we had, so there's a 12 and 5, right? So let's talk about only the first bit. The first bit, and next state 0, right? So that should be really set, right? So which is the high priority? It's a reset, right? If the reset equal to, let's say 0, right? We said not reset. If the reset equal to 0, the value should be 0, right? Output. Simply I'm just, kind of having a multiplexer. If the reset equal to 0, the output is 0. I don't even look at the other side. So now if you look at the code, right, we had, the preference or the kind of priority. The first one is a reset, and that to be, it should be 0. The reset, it should be 0, right? If it's 0, then its output is 0. I don't even look at the other parts. Okay, now if the reset equal to 1, if the reset is not active, so then the next priority is given to set. If the set equal to 0, right? Then what is output? It's a 1. So I'm just simply connecting to 1, right? So now this 1 will be connected to the next state 0. Now if both are not active, that means if both are 1, 1, right? So this is 1, this is also 1, then only I'll come to the D flip-flop, right? Simply, it's a clock A, and then I'll just read this output. Now you see, right? So this 0 and 1 just connected to 0 and 1 here. So what I need to do is that simply, right, I have to really replicate this whole structure. Okay? This is for the next state 0, the next state 1, and the next state 2, and the next state 3. Right? Now you tell me, is it difficult? So as I said, right, so we need to just understand, some of these, how the tool does for this, some of the simple examples. And then, so we would be able to also really draw all the complicated logic, even given, a simple, background about, the Boolean equations and the truth tables. Okay, good. Now, okay, so maybe what I have is, okay, now, okay, right, so this I copied from a book, yeah. So basically, if you look at maybe this circuit, right, so he was trying to really use, maybe, some kind of a circuit set. So this NR2, NOR gates and all, right. Again, maybe for the library which he was using, right. So here this, let's say, NOR2 gates and all, right. But later on, once I pass on the slides, you try to get the D logic, maybe the PD logic, or maybe this PDN logic here. So it should really match exactly. It should match exactly for the kind of the circuits we derived. Okay, good. So now just one more concept which I want to discuss. Okay,
So now, what is the difference between the previous circuit and this circuit? Okay. So here again, we have always the negative of clock B, right? So whenever we have this passage of the negative of the clock, definitely we are going to get at the flip-flops for the left-hand side variables. That means the next state is going to be a flip-flop. Now, what is the difference is that, so the reset and set are now going to be synchronous. So that means, so they should also be evaluated with respect to the clock input. That means, right? So if you have a D flip-flop, right? So this is your, let's say, negative of the clock, right? The clock B, so this is a D input, right? Now, we should really come up with a combinational block, so which will take the reset, set, and maybe your this current state, and then connect it here. So now we don't have any kind of reset and asynchronous reset and reset pins. Okay. So here, so that's what I'm trying to really show. So here again, I wrote the same circuit. Okay. But now if you look at here, okay, what I did, I'm trying to really redirect this whole logic of your set and reset to the D input itself. Right. So now the D is synchronous with the clock, right? Now if you look at here, right, if the reset equal to 0, my input should be 0, right? So that's what I said. If the reset equal to right 0, it should be 0, active high. If the reset is not set, the next priority is set, right? If the set equal to 0, it should be 1. It's a 1. Yeah. If both are not set, so 0, right? So that means it should be 1 and 1. Then only I'll take the current state. Now, if you remember, right, if it is a synchronous, this whole logic is really coming here to the D input. If it is asynchronous, this whole logic really coming, maybe after the flip. Right? So now, I mean, this how kind of your synthesis tool really behave. So when it comes to synthesizing this, flip flops and latches and all. Okay, good. Ma'am, how much time I have?
Sir, probably it's 3:05. Is it possible for you to wind up in 5 minutes? If it is possible,
yes, ma'am.
Then that will give us some time for the Q&A and also running the quiz.
Yes. Okay. Good. So now,
if it is possible, hopefully.
Yes, ma'am. Yes, ma'am. That's, I think that should be fine.
Yeah.
Okay.
So participants, if there are any questions, kindly collect your thoughts and start putting the questions in the chat box, so that we don't have to waste time in prompting you to put the questions.
Okay. So now the same thing which we can really do for the flip flop, let's say latch as well. Okay. Now if you look at this part of the logic, right? So we don't have anything like passage of the clock or negative of the clock. Okay. Now we can safely say that it's not going to synthesize as a flip flop. Now let's look at maybe this loop. Okay. Now if you see here, if we are mentioning something, else if we are mentioning something, else if. But now if these are not, let's say, true. So what about the else block? Right? So now, as I said, some conditions you are mentioning and some condition you are leaving it out. Okay. So now in this case, what is going to happen is that the next state is going to be synthesized as a latch. Okay. Now whenever we talk about a latch, right, again, so what we have in mind, let's assume a D flip flop, right? That's a D latch. We have a Q output, right? And then enable pin. Now again, the question is, so in this case, again, we have not reset and set pins, right? Okay. So maybe we'll have maybe this PD pins, CD pins, set pins and reset pins. And then what gets connected to here? What is the logic we should have? What is the logic we should have? What is the logic we should have? Now everything it really comes from here. Okay. So now again, like we can think of so why do you really use maybe the PD pins or CD pins? If one of them is only needed, we can only use one of them. Yeah. Right. And what is the guarantee that now we have an active high? Let's say this PD pins, active high CD pins. Maybe we have active low, let's say PD pins or CD pins. So we have to modify our logic. And now it could also happen that we don't have a, let's say, latch with this PD pins and CD pins, right? So again, right, so we have to use only simple D flip flop as a D latch. But again, so since this is asynchronous, right, So we have to, let's say pair up, our, let's say, muxes, as we did in the case of, let's say flip-flop. Okay, good. So now, just to conclude, maybe, so as I said, so I just wanted to, kind of clarify that. So as I said in the beginning, so this, I mean, if you wanted to really teach the Verilog and, the proper syntax and all, right? So it will take, kind of a really kind of a long time to really, we've run a kind of a semester long course. But what that I was trying to really do is that with the simple examples, okay, if you know simple K-maps and drawing truth tables and, ask these questions, whether we get a flop or a latch, whether it's a full combination logic. These are only the 3 questions you should ask yourself. And then by using this simple K-maps and all, we will be able to derive the whole logic corresponding to your Verilog circuit. Okay. So, ma'am, I'm done.
Thank you, Sujata. Sujata, unmute.
Oh, I'm sorry. I was talking
You were
without.
talking without unmute.
Yeah, I didn't realize it. Sorry about that. So thank you, Professor. Thank you for a wonderful session. So participants, I hope, the interest in designing this, all these digital designs, which Sir's professor has shown would have, kindled more interest in learning this session, a topic in more in detail. So if there are any questions from the sessions that you have heard today, we are open for the Q&A segment. We would like, as I mentioned earlier, you can post your questions in the chat box, or, even better, I would, sir, we have been hearing only the professor speaking all the while. So we would like to hear a different voice. So you can raise your hand and we'll unmute you and you can ask your questions. Sir, there are a few questions already in the chat box. So I'll just read it out one after the other. As we get more questions, we'll handle them.
Right.
This is one question from Dr. Shagun from Kathmandu Engineering College. His question is, we have learned the code combinational logic, flip-flops, etc. using Verilog. Is it possible to code the microcontroller or microprocessor or any sensor block using Verilog?
Yes, okay. So now let me ask you this question, or let's think through. Okay, now any given logic, right? So either it should be combinational or a sequential logic, right? Even if you look at maybe memory, a microprocessor, a microcontroller, anything, right? So if you deep dive into the architectural details, right? There are only 2 types of circuits, let's say, present in the let's say the architecture. Yeah, either it's a combinational or it's a sequential. Okay, now there could be multiple combination circuits working together, or the multiple sequentials, let's say kind of FSMs talking to each other working, right? So for instance, if you talk about 8085, right? So we have some kind of timing and control unit, right? So with respect to some clock, it's generating read bar signal, write bar signals, or maybe ALE signals, right? So basically, that is a pure state machine. That means it's a sequential machine. Okay? So maybe if you look at the ALU, right? So what the ALU is doing, right? So one is your accumulator, maybe it's according to the instruction, it's maybe reading from B, C, or maybe D register, maybe adding subtraction, right? You can think of it as a combination block, right? So now to just answer your, let's say, question very directly, once you know the kind of how to code a combination block and how to code a sequential block, right? You can in fact code anything. And actually, right, there's no other, let's say, block in the digital design. Either it could be a combination, it could be sequential, right? So that means we can code anything you want. Ma'am, the next question.
Yeah, there was only one question. I think Priyadarshini was trying to answer. Any other questions, participants? So the session becomes interesting and informative only when you ask and interact. So don't hesitate. No question is a big question or a small question.
So we can code, okay.
Kishore, you can meanwhile paste the Slido quiz link also. As we wait for the questions, you can paste the Slido quiz link. Yeah, there is one question from Rupesh. How does one optimize Verilog code for synthesis. Are there specific coding techniques or constructs that lead to better resource utilization or performance on FPGA or ASIC?
Okay. Okay. Yeah. Now, so to answer that question, ma'am. So, for instance, maybe I'll just use again the slides. Yeah. Or maybe the notepad. Okay. Now, right. So here, so suppose there is an expression is equal to a bar b plus ab bar. Let's say ab. So what is the value of this one? Right? It's a f equal to 1, right? Because let's say f is a function of ab, right? And of course, all the minterms are there. It's a 1, right? So there's no need to implement. So, but now, how does really, the logic or the circuit really figure it out? Or maybe the tools will really figure it out. Right? Maybe being a human, now you are saying that, okay, so f is a function of ab. So we have this one minterm and the second minterm and the third and the fourth one. All the minterms are present. So basically, right? So we have a, let's say all ones, one. Let's say all one, it's a f equal to 1. Right? But now, how does really, the tool will figure it out? Okay, now the tool uses, what is known as, there are a lot of the techniques. Yeah. So one of them is your kind of a, what is known as a binary decision diagram. Okay. So when such kind of logic is built, now in my, let's say, slides and all, right, so we're trying to really build the logic. So we did not really talk about the, let's say, the optimization. So let's say one of the logic is build something like this. What the tool does is that, so here, so we have a, right? Okay, so a can take a value of 0, a can take a value of 1. Again, so b can take a value of, let's say, 0 here and a 1 here. Again, once a took 1, we can have a b value 0, b value could be 1. Now, according to this, let's say, diagram, right? Everything is a 1, right? So here, it is also 1, this is also 1, this is also 1, and this is also 1. Now, if you look at, so what is happening is that if I go to the B and look at the left child and right child, so they're going to the same, right? So then why should I have the B here? So what I'll do is that I simply really replace this with like this. Okay. So now if I look at again this B, right? Okay. So left child or the right child going to the same one, right? I'll remove this one. I'll just replace with the 1 itself. Okay. Now again I look at here, right? Okay. So whether the right child or the left child is really going to the 1, right? So basically, now, instead of implementing this whole thing, this function really simply pointed to 1. So this is how, the optimization is really implemented, in the tools and all. Okay, just to give you an example, this is one of the techniques. Yeah, but there are like something called, sub-expression, elimination, substitution, and all those things. Yeah? If somebody is interested, right? So there's some book called Digital. Forgot, but so it's a Giovanni Initially, yeah, maybe the spelling might be wrong, but okay, the book by Synthesis and Optimization of Circuits by Giovanni Dimicheli. He is a professor in EPFL. So maybe you just Google for it, so you will get his book. Okay, so some of these techniques are really described in the book.
Thank you, sir. Rupesh, I hope it answered your question. If you have any follow-up, please let us know. There is one more question. Which is better, Verilog or VHDL referring synthesis?
Okay. So now, as I said, so it's just a kind of a choice of the people. Yeah. But now, if you look at the European market, right? So they use the VHDL. Okay. And of course, right? So the circuits equivalently optimize the VHDL circuits and the Verilog circuits. So the problem with the Verilog is that, so Verilog, right? Of course, right? So since I think, after Verilog 2007, it's not developed further. So what we have is only now the system Verilog, right? Okay. So now, but if you look at maybe the VHDL and all, right? So there is something called, data types which are related to like kind of, structures. Okay. Now you might be kind of, heard about packing and unpacking arrays and all. So maybe the Verilog was not really developed after, let's say, 2007 or 9, right? So now it's only the system Verilog. Of course, right? It's a kind of advanced version of Verilog, right? So I would say that, it's again the choice, but the tools, right? So, as far as I know, they synthesize both the logic, kind of, equal. It's not like, so VHDL circuits get optimized more compared to, the Verilog or something like that. Yeah.
Okay, sir. Why do we always use the @ symbol in behavioral modeling coding, model coding?
Okay. Now, so for instance, I just said, if you do not do always,
We lost, sir. So just give a second. I think
Unmute. He's speaking, but we are not able to hear it. Unmuted
no,
accidentally.
hold on.
We will take the quiz together, so don't be impatient. Wait
The
for
screen
the.
is frozen actually. The screen is frozen.
Could you tell us which platform?
Yeah. Sir, are you back? Sir, are you
I
back?
think,
Yeah.
Yeah.
Now we are
We are
able.
able to hear you
you're
now.
able to hear me, ma'am?
Yeah, we are
Yeah.
able to hear.
We are able to hear you now.
So I think, so I had a problem with is it better, ma'am? No?
Yes,
Yes,
it's
sir.
better.
We are
Okay.
able to hear you now. Yeah.
Yeah. So now to answer that question, right? So the Z is being assigned, let's say when, the question is when. So whenever there is a change in A and B, then only you should assign, let's say Z, not always, right? So that is the reason we mention, always at the rate, A and B. If there is a change in A and B, then only we should assign Z. Okay.
Yeah. So the next question is, which platform can we use as a beginner to practice Verilog?
Okay. So the simple, the best would be the Verilog, okay, and the GTK wave, and then you should really start with, the Verilog HDL by, Samir Palnitkar. So now, and that book has a kind of a very easy explanation, and there will be kind of a lot of, examples in the beginning. So the best thing is to really practice. And
Thank you,
for the
sir.
synthesis part, so there's a book by, the Bhaskar. So that is only the book available. So Verilog synthesis by Bhaskar. Okay. So
Yeah. So we'll share the recording of this session. So all the names and authors that Professor has mentioned, you can still retrieve it by hearing to the session once again. Or
so,
you.
ma'am, I don't have a problem in sharing the slides. Yeah.
Yes, sir.
Even that, the notes which I, used, with the OneNotes. So maybe, they can also really cross check, what I said. So maybe I'll also share those OneNotes, and that can be also shared.
Very nice of you, sir. We'll do that. Thank you. So all the presentation and the notes from the session with the recording will be sent to all the people who have attended the session today. Or rather, marked your attendance. Attending in Zoom is not the criteria. Mark your attendance. The next question is, how can Verilog be effectively used to design digital controllers for battery management systems in electric vehicles?
And again, so the same question, ma'am. So it doesn't matter what is the application field, right? Again, now if somebody is trying to architect the controller or whatever, right? What it boils down to is that either it should be the combination logic or the sequential logic. So now there are only two types of sequential machines, right? We have the Mealy machine and Moore machine. If you know how to code a Verilog for the Mealy machine, and how do we really code for the Moore machine, that's all, right? So now only thing is that whether your state machine is optimized or not, that's again a separate question. But once you have an optimized let's say the state machine for your controller, so there's only one way of coding the settling, let's say the FSM. Yeah. It doesn't matter. It doesn't really kind of depend upon the application, right? So, right. So anything can be coded. Yeah. So you should only look at any application as either it's a combination or a sequential or the combination of both.
And last two questions is the future of VLSI with Verilog and use of Verilog in IoT.
Okay. So now I would say that since I already mentioned, so since 2007 or 9, the Verilog is not really developed for it's a system Verilog, right? But once you understand the Verilog, let's say understanding the system Verilog, it has a lot of other features. Yeah. So that would be really make easy. So I would say that, so being a kind of, the bachelor student, right? So you should be really kind of, kind of familiar with let's say Verilog. And then if it is a master level course and all, right? So maybe you should also kind of a transition into, a little bit of system Verilog, use the advanced features.
Any other questions? Anybody wants to interact with the professor? Not every day that you get a chance to interact with an IIT professor. Anybody wants to ask questions directly to sir?
Dr. Gomatish.
I think there's what are the use of Verilog in IoT, right? I mean, again, so wherever the hardware, you wanted to design, the Verilog comes into picture. So if IoT has some kind of, embedded system, which are maybe, a microprocessor or embedded controller. So definitely, somebody would have used, let's say, the Verilog or, similar languages to really build it. Okay. Okay.
Thank you, sir. So what we will do is we will have the quiz session now, and then, if there are still further more questions post the quiz, then, we will take them at the end of the session. So participants, Kishore, can you repost the quiz Slido link? See, we have posted a Slido link. I have not enabled it yet, the quiz. So don't get apprehensive that, the quiz is not there yet. I'm going to share a screen. There are a few questions here. Okay, anyway, I'm going to, I hope all of you are ready. So what I would request you is, the link will take you to your browser. For the next 4 or 5 minutes, you need to interact only with the browser. So don't be on the Zoom screen. And, when I tell you to come back to the Zoom screen, that is when you have to come. So now, if the quiz is appearing on the Zoom screen, it is for the professor and PALS members to see it. We are only sharing the screen here. So if the screen in Zoom is not interactive, you have to be on your browser. So I'm going to post the first question. Let me see how many of you have first joined into the quiz. Dhanush's question is, I want to become a physical designer. Can you suggest some references? I don't know what kind of reference that you're looking at, Dhanush. You're asking for some company name, or what is that you're asking?
Ma'am, just maybe let me put it this way, that those who know about the C2S program from, let's say, the MIT, the Ministry of Electronics and Telecommunications, yeah. So they do really conduct, I mean, these days is very quite often. So maybe you should really get in touch with, one of the institute where the C2S program is running. And then, so, I mean, of course, right, in the physical design is really kind of, very big. The synthesis there, kind of a floor planning, placement, routing, there are a lot of other things are there, the physical verification, yeah. There are a lot of other things are there. So, one can really cover that in a kind of, overview itself, maybe, it takes too much time. So what actually the C2S people does is that, so they will have some kind of a sessions for each topic, let's say synthesis or floor planning or routing, yeah, maybe the physical verification. So maybe I would suggest that, okay, just to get a feel of it, actually, what exactly these terms means and how the tools are really doing these, the activities or the tasks. So maybe I would request that maybe you should get in touch with, the nearby, the C2S coordinator. Okay. So mostly, of course, IIT Madras also has, the C2S program, and we do have, and even some of the colleges, in and around you might have the C2S program and the coordinators. So they will be getting, kind of a links or maybe the dates for, on which day, this kind of a training is happening. So maybe, you can join those sessions.
Sure, sir. Thank you. So I'm going to, there are 475 participants and probably 368 have joined. So I'm going to start the quiz. The first question will appear to you now. I hope you're all able to see your first question. electric bulb filament is made up of? It's a 20 seconds question with 4 options. Okay, so I see option D has been chosen by 94% of you. And let's see if that is the right answer. And yes, that is the right answer. Now, this was not a question from the session. It was not given by the professor. I've just included it for you to get a taste of how this whole thing works, basically. We'll just have one more practice question and then we will go into the actual quiz. So one more practice question for all of you. I hope others who have not joined yet, I see that only 285 of you have joined, have been able to answer this particular question. So make sure that you're prompt in answering within the 20 seconds. The next question. What is the expansion of PALS? So it's an opportunity to know what PALS is all about. I would like to know who the 3% is, because the right answer is option C. PALS has no expansion. PALS is basically PAL as in a friend. That's it. So please remember that next time onwards. And then we will get into the actual quiz now. So here comes the first question from the session today. Be quick in answering. It's a time-bound quiz. %78% of you have said all of the above, and that is the right answer. Moving on to the next question. Okay, there's a mixed response here. There is a confusion between B and C. And the right option is B. 35% of you have got it right. Sir, is there anything that you would like to clarify in this particular answer because of the confusion?
Not there.
Okay, I'll move on. I think sir is not available. The third question. Okay, we have option C, 62%, and that is right. Now, don't close your browser. Just come back to the Zoom screen. If you can come back to the Zoom screen, you'll find that Ishwaran, Sharan, Priyakant, Jnanasai, and Mohammed Ibrahim. And I don't even know which college all of you are from. It would have helped if you could have put your prefix or suffix to your college name. So all of you have got, the full, all the questions right. And then why is Ishwaran at the top? It's because of the fastest finger. He's answered all the 5 questions in probably around 1 minute. So the leaderboard position may not remain the same. Please go back to your browser. I'll give you a few seconds. Be ready for the next set of questions.
Ma'am, professor has raised his hand.
No, I have unmuted him already.
So sorry, I got it's a blue screen, ma'am. All of a sudden it restarted. Yeah.
Oh, okay. Yeah,
Not
I
a
have
problem, sir.
unmuted your thing. You requested for unmuting.
Yeah, good.
So,
I will move on with the quiz.
Sujata, that question. Okay.
The fourth question. Anu, we'll get back to that because I can't go back to the previous. Option C is the right answer. Good. The next question. Here only 26% of you have got it right. The answer is option B. Moving on. Okay, and the right answer is option B. 47% of you have got it right. And the leaderboard position, Sharan. Sharan has managed to get all the questions right in 2 minutes. Congratulations, Sharan. Which college we do not know, followed by Deepan, Jnanasai, Sanjeet, and Mohammad Ibrahim. Few of you are there in the top position from the beginning. So this was the interactive quiz. Thank you all. I hope all of you enjoyed. If there are any further questions, anybody wants to ask questions? Any questions do we have?
So, ma'am, just I have only one suggestion for the participants. Okay, so there are a lot of kind of material available, maybe on the Verilog parts itself. Okay, so it's not about the covering the syntax and all those things, right? But whenever you read something, right, you should always think about what comes out of the code. So many students, what happens is that they try to simulate it. Okay, now in the simulation it corrects. Let's say the values, everything is the results are really correct. But when it goes to the synthesis, you have a problem. You think that flip flop will come, but the latch will come, and the behavior is completely different. So now what I would suggest is that you should always think about what comes out of the circuit. So whenever you learn something, right? Okay, now how do I draw the synthesized circuits? That's way you need to practice. That's what I was trying to really do it actually in the last 1.5 hour.
Thank you, sir. It was a wonderful session. So I request Anu to come again and then conclude the session. Anu?
Yeah, thanks, Sujata, and for a wonderful session, Professor. I have quite a few takeaways from this. It's either combinational or sequential. You learn which one is asynchronous and which one is synchronous, and a lot of new jargons that I picked up today. And my understanding at this point is we can optimize any circuit. It's a good way of minimizing the hardware that you use in your design by using something in simulation, like in this Verilog design. So is my understanding right? Then
to some extent, ma'am. Yeah. So in a simulation, we cannot really do it. But as I said, in a synthesis tools, definitely we can optimize.
Yeah. When we synthesize, we try to reduce the number of gates in it, and then hardware naturally reduces, and the cost will reduce. But we have to be right. So our understanding of the logic and the basics should be right, so that we are there. And with the semiconductor industry booming in India, I hope all these people here will make use of things that they heard right now in connection with whatever they learn in their classes, and make good use of PALS lectures when they come from professors like you. And thank you so much for your time and simplifying the whole semester credit into 1.5 hour or 90-minute session. I think this is really a 30,000 feet overview of the whole subject. But then if one is interested, they can always get motivated and do some great designs in future. So thank you so much. And thank you, participants who are part of this particular very first lecture of webinar of PALS. And thank you, faculty members who had stayed up and then asked the right questions, and the students who had asked some very good questions. I hope you take a lot from this with your basic knowledge. You're so much closer to the knowledge input at this point of time. You'll be better than me in having better takeaways from this. So I will look forward to your feedback, and you're taking the online test so that you'll be eligible for a certificate of participation in this program. And thank you, Sujata, as always, and the PMO for being there and the interactive sessions. Thank you very much.
Okay, yeah, thank you.
Thank you, sir.
Yeah, thank you. Bye.
Thank you. So participants, what comes next? We have given you a feedback form. We have given you a post-session quiz. It is an interesting quiz, take it right away. Don't postpone it. Mold the iron when it is hot. It is fine. I mean, you'll be able to mold it better. So hit it when it is hot. The feedback session has a feedback question. The form has a question. Do you want a sequel to this particular session? So if you feel you want to learn more, kindly, give your feedback. And that is also a better way. Feedback is just not for us to know how the session went, but it is more a reflection point for you on knowing what are the things that you have learned and what are the takeaways, basically. Okay. So hope all of you had a great session. Thank you all. And we'll see you in the next PALS program. Ensure that you give your attendance, feedback, and the quiz. Thank you. Kishore, first you should stop the session and the YouTube live stream.
I will.